Our next keynote speaker is a senior staff site reliability engineer at Google and has spent the last 9 years improving the security posture of Google's infrastructure. As the production tech lead for security, he is responsible for the harmonious collaboration between the SRE and security organizations. In his previous role, he led a team responsible for the reliability of Google's critical security infrastructure. Before joining Google, he built a startup, worked at CERT Polska, and has received a degree in computer science from the Warsaw University of Technology. As he joins us on this platform, he would be enlightening us on the lessons he learned that allowed him to build and maintain secure and reliable systems, as well as some design principles he followed that made it possible. Ladies and gentlemen, I'm delighted to have with us now the one and only Mr. Piotr Lewandowski.
My name is Piotr Lewandowski, and I'm a senior staff site reliability engineer at Google. For the past decade, I've been working at the intersection of security and reliability, and today I wanted to talk about how to build and maintain secure and reliable systems. I'll share some of the lessons we learned at Google and some of the techniques that we're using to build trustworthy systems. Let me start with a story, and to tell the story we need to go back to 2012. And Google has an internal password manager that allows employees to store and share secrets for third-party services. Google also operates a network of buses in the Bay Area, so that connects all the campuses in the region together. On those buses, there is a guest Wi-Fi system that employees can use to work and access the internet. Transportation teams that operate those buses emailed thousands of Google employees that the Wi-Fi password has changed and instructed them to go to this password management system that we've built to fetch the new password. Now, the important thing to understand is that this password management system has been designed with a completely different audience in mind. It has been developed a few years back for a small audience of system administrators. It was not designed for like thousands of users. So the spike in traffic was larger than expected, and it caused actually the primary replica of the service to become unresponsive. Load balancer decided to divert the traffic because the primary replica wasn't responding, diverted the traffic to a secondary replica, which failed in the same way as the primary one. At this point, an on-call engineer in New York got paged, and it was turned out to be a bit problematic because they had no experience responding to failures of the service. The service, in its 5 years of existing, never had an issue. It was, a niche service used only by a handful of people. So there was really no a good experience how to handle those type of scenarios. The intuitive way was to restart the service. Unfortunately, that failed because what the engineers didn't know that restarting the service required actually a smart card inserted into the hardware security module of a server. And now those smart cards are stored in multiple safes across the Google offices, but not on the EU East Coast where the on-call engineer was located. So he had to actually reach out to a colleague in Australia to retrieve that smart card. And then it turns out that we have a second problem, might be a bigger one, because the combination to the safe in Australia was stored in the password manager that just went offline. So obviously it wasn't possible to restore the smart card. Fortunately, there are a couple of Google offices that have those smart cards, so Australia wasn't the only one. They reached to a colleague in California who actually had memorized the combination to the safe and was able to fetch the smart cards. After inserting those smart cards into the reader, the service still failed to restart. It produced a very cryptic error that wasn't really meaningful in any sensible way. And then engineers realized that we need to fetch another set of cards because those are faulty. So the story went back to Australia, and now, given that the safe combination is in password manager, well, they decided to use the last resort action and apply the power drill to actually break the safe, drill into the safe, and fetch those smart cards. Which, after an hour they did, they managed to recover those smart cards in Australia successfully. They inserted that to a smart card reader and nothing worked. It gave exactly the same error. Only after an hour later, they realized that the green light that was attached to the smart card reader didn't indicate that the smart card is inserted properly. Actually, what happened is that the smart cards were inserted upside down and the green light still came up. Obviously, when they flipped the smart cards, everything started to work again and the service got restored. Outage has ended. It might be a bit of a silly example, but I think it illustrates a couple of points I want to talk about later. And before we move to the differences between security and reliability, it's important to notice that both are quite similar, actually, and both are crucial components of every trustworthy system. Unfortunately, building systems that are both reliable and secure is quite difficult. The requirements for security and reliability have common properties, but they have also different design considerations, and actually the interplay between security and reliability can be quite subtle. It can be easily missed. And for example, in case of the example that I gave about the password manager, the failure was triggered by the reliability problem. It was a poor load balancing and lack of load shedding strategies that caused the primary replica to go down. Recovering from the state was made much more difficult by a security measure that we had in place, that the passwords were actually protected by a hardware security module. So it's important to realize that both security and reliability can have the subtle interplay that will actually produce unexpected outcomes when not designed carefully. The other aspect of it is that it's both properties are not really visible if everything's going well. So, for example, in the power drill story, the on-call engineer got paged and didn't really know what to do. The service has been operating for 5 years without any problems, and even though they were reliable and there were a reliability problem due to lack of load shedding strategy, they remained invisible. And there is always a risk with those invisible properties. When there are no emergencies, they can be seen as costs that can be cut. So it requires a constant attention and being very mindful about those properties that are very difficult to bolt on after the fact. That's another common characteristic between security and reliability. Both need to be taken into account from day one of designing a service. Otherwise, it will be very costly or nearly impossible to add them at a later stage. Just like you probably wouldn't buy a car that had safety belts added as an add-on at the very end of the production process and not being taken into account from day one. It's very easy for system changes to affect and worsen those properties. So both security and reliability are those emergent properties that can be easily disrupted by potentially innocent changes, as they are determined by interaction of multiple components. Now, the biggest difference between those is, I would say, whether there is a malicious act or not. The reliability risks are non-malicious in nature. So, for example, it can be a bad software update, a physical device failure, acts of nature, disasters. Security risks, however, are quite different. They come with an adversary, who is usually a human still, and that are actively trying to exploit system vulnerabilities. Sometimes from the victim perspective, it can be very difficult to distinguish between both. For example, a DOS attack can look very much similar to a popular spike because the product got published on Hacker News or Slashdot. The other implication of this, the other difference between those two, which is implication of the previous one, is how we design system failures. So if they fail, do they fail open or do they fail close? Because they can respond to failures in quite different ways. So in the absence of adversary, the systems usually fail open, fail safe. For example, an electronic lock door, in case of power outage, can be designed to remain open so that people can exit safely through the door. While fail-safe open seems like a good idea, it can also lead to obvious security vulnerabilities. So, for example, another aspect of it is redundancy. Usually, if you want to have reliable systems, you add redundancy. So next to electronic lock, you can add a physical lock that can be operated when the electronic lock doesn't work. Now, while it improves redundancy of the system, it also increases the attack surface, because now adversary doesn't really need to interact with the electronic lock at all. Perhaps all they need to do is to pick that physical lock that has been installed or steal the key. The other aspect of differences between reliability and security is transparency versus secrecy. In case of, for example, handling a crisis, you usually want to have all hands on deck, so everybody can work to diagnose and mitigate the root cause. And the more people with different perspectives you can bring to the table, the better, because it means that it could potentially lead to the resolution faster. Now, with security vulnerabilities, it's a bit different. If you have a suspicion of a security compromise, you usually don't want to have like a very broad announcement that it just happened. You don't want to tip off the adversary that there is an investigation going on and they have been caught. You usually want to restrict the circle of people that are investigating the system to the smallest circle that is effective at mitigating and containing the compromise. And both properties are increasingly important, especially like this year has proven that people do rely on technology to stay connected despite pandemic, and the more trust we put in those systems, the more trustworthy they need to become, the more reliable and secure they need to become. And it wasn't probably ever more true than it is in 2020. So obviously absolute security and absolute reliability is not achievable. It's a good North Star, but no amount of money will us get there. So it's important to set some goals, realistic goals that we can aim at. In the reliability, the SLOs are a popular concept. So we set service level objectives, and those are thresholds above users are happy and they want to use our product, they recommend that product to others, and below they will go to our competitors, they will get fed up and leave. Obviously customers are different. No SLO will probably meet everyone's requirements. So you can imagine you have a product which, on one hand, some users want to have like low latency properties from that system, perhaps in a hot path of serving user data. On the other hand, there might be a class of users that do offline processing, and they don't care as much as about latency as much as they care about the throughput. And those different customers have different needs, and there is also different cost associated to running those systems. Systems that require low latency need to be under-provisioned so that they can handle spikes well. Systems that do batch processing can be over-provisioned so that they can go through the backlog in a reliable, predictable way, but some queuing is not a problem. In terms of reliability, the other mechanism that we recommend to use is error budgets. Error budgets guide us when it's safe to roll out new features and to make more risky changes. If the service has been reliable enough that it's overshooting and overachieving its SLO, then perhaps there is some wiggle room and perhaps there is some risk that we can take to push new features. On the other hand, if the service was struggling and maybe there was an outage, maybe for a while we want to focus on reliability and we want to freeze some feature rollouts, and that's why our budget comes into play. Security is a bit different from security. The important part is to assess the value of assets that you have. So basically estimate which parts of your company are valuable from an adversary perspective. Which parts of your company, where it's user data that you process, maybe it's intellectual property of your business, maybe it's a database of your customers. So I would recommend putting value, trying to put value on that, and try to figure out what the adversaries might be interested and after. And obviously, it's impossible to achieve perfect security, and while it's good to prevent as much scenarios as possible, it won't be always economically viable to do so. And in those scenarios, you might settle for detection. So instead of preventing some perhaps rare scenarios, perhaps it's good to invest in detecting those scenarios, if not preventing. There are a couple of design principles that we can follow while designing and building a new system. First, and I think the most important principle to keep in mind is simplicity. There are many of them, but I will just mention three. So simplicity is about keeping the system design as simple as possible. And it's one of the best ways to improve the ability to assess both the reliability and security of a system. This also leads to creating systems that are more understandable. So it's easier for a human being to comprehend what is going on. And that's especially valuable in case of emergencies. If there is a security compromise, or if there is an outage, having a system, a reasoning about the system that is understandable becomes much, much easier. And it will lead to reducing the time to mitigation. Now, no matter how simple the system becomes and elegant at the beginning, it's very rare that it will remain unchanged over time. And there is a market pressure demand that can lead to cutting some corners and accumulating technical debt. So the other thing to keep in mind is complexity usually doesn't happen overnight. It's being accumulated day after day, month after month. And sometimes it can lead to a tipping point situations where a small incremental change can have a dramatic effect and compromise the reliability or security of a system. So one of the examples was the OpenSSL library that was distributed in Debian back in 2008. Two lines were removed from OpenSSL to address some Valgrind warnings about using initialized memory. There has been removed. Unfortunately, the consequence was very severe. It made keys that were generated using this library easily predictable and result in a major vulnerability. So we can imagine like a very small change. It was innocent looking on its own, but it had tremendous consequences. The other design principle worth keeping in mind while designing a system is resilience. So systems should be designed that they can stand on their own under adverse or unexpected circumstances. And obviously this can be done to some extent. So you need to take a look at multiple aspects of a system to do so. For example, in terms of designing a system that is resilient from overload, it's useful to think of a load as a function of the volume of the request and the average cost of a request to the system. And when the system gets overwhelmed with too much load, it can decide to do one of two things. It can either reduce the volume of the request by doing load shedding and dropping some requests, maybe low priority ones, or it can reduce the average cost. So maybe the response will not be as featureful as designed, but maybe we can serve a degraded response that is much easier to compute. maybe some stale data with a warning that the data is not fresh. The other aspect of building resilient systems is addressing component failures. So obviously, you don't want to have single point of failures in your system. You want to incorporate redundancy and distinct failure domains so that even if one is compromised or fails, it's easier to sustain the operations using the remaining failure domains. This is both reliability and security technique to create those compartments that are independent of each other. But unfortunately, once systems become sufficiently complex, it becomes almost impossible to demonstrate that the entire system is immune to compromise. So to address this, we use a technique called defense in depth, where we deploy multiple and sometimes redundant overlapping defense mechanism. That allows us to limit the blast radius, and it also increases reliability, usually. One of the examples I can give is, for example, introducing multiple layers of encryption. You can imagine that we want to store data on disk encrypted. In case the drive gets stolen, the adversary won't be able to access our data. Now, usually drives come with a hardware encryption. We can use that. That's a good idea. But perhaps we want to encrypt this data ourselves before we put it on an encrypted hard drive, so that we have two layers of encryption. And if one is compromised, we always can fall back on the other. So that's one example of defense in depth. And the other technique that we sometimes use is least privilege. This actually is also a reliability and security mechanism where we only grant capabilities or privileges that are needed to do a job at the given time and not more. So you can imagine that every now and then you need to do some administrative operation on a database, but in the regular course of the day, you don't need this capability. And this is how we design our systems at Google internally, that users do not have all the privileges that they need for business all the time. They only request it for this short time window when they really need it, and that's it. And a similar concept is with Zero Trust. We try to put as many proxies as possible to enforce some of the security and reliability mechanisms, safety boundaries in the proxy. So we put a proxy between a human and the system that is being changed to enforce some safety limits. And to a similar mechanism using humans is a two-man rule. This is a old rule, older than what we call a modern IT. This rule has been used to manage nuclear weapons, for example, or bank vaults. So you need to have like two people, usually a requester and approver, and they need to agree to take an action. Only then, if two people agree, then only then this action is actually effective. There are also some principles that can be applied while implementing a system. So the previous ones were about designing a system. The current ones are about building a new system and translating the design into a fully deployed system. So when you build a system, it's much better to use standardized battle tester frameworks and libraries and not necessarily implement your own. It will save you some time. It might be less exciting than writing a new thing from scratch, but it's usually better off in the long term. The most popular example is the popular catchphrase, don't implement your own crypto. It's always almost a bad idea to implement your own crypto. Testing is also a very important component. You can ensure a lot of properties through continuous testing. So for example, like load testing to understand how the service behaves under a flood of requests, fuzzing to explore the behavior of unexpected inputs, and specialized tests, for example, that ensure thread safety or no memory leaks. Deploying code is another step, another place where you can enforce some safety and reliability properties. So in reliability, you can do slower rollouts with canaries and automated rollbacks that prevent you from breaking a system for all users simultaneously. This obviously requires some discipline so that no code is backwards incompatible. You can always roll back if needed. A security example would be deploying code that has been signed by the build infrastructure, so not accepting binary blobs from any source, but enforcing that the binaries that are deployed into production environment have no provenance, have no audit trail. The other step is logging. Usually we want to log as much as possible. Good logging is foundation actually for detection and forensics. There is a tipping point where it might be actually more attractive for an adversary to go after logs than a system, because if the system is logging sensitive information or like personally identifiable information into logs can become a target itself. So there is some balance act needed to weigh those pros and cons. Crisis response is a super important topic. Organizing response is challenging as it is, and it's best to do it before the emergency occurs, because emergency usually means chaos, and it will be much more painful to do it during the chaos. What's really crucial in this stage is clear roles and clear chain of command, so that everybody knows who is accountable and who is expected to make decisions. At Google, we use a model called IMAG that we modeled after US government's ICS incident command system that is used by first responders. And we use it all the time. We use it even for small incidents that do not warrant like full-blown IMAG response, but we do it to practice, so that IMAG doesn't remain a concept that is just written down on paper. It is a live concept that is tested and practiced on a regular basis. For long-lasting incidents, it's important to take into account that you might need to rotate shifts and do hands-off, especially if you have a globally distributed team. And between those outages, between those crisis responses, it's important to allocate time to test and improve the procedures so that people don't have to figure it out when emergency comes. And the last aspect is recovery. Recovery is ability to recover systems after a destructive action. So, for example, the rollback, safe, always available rollback option that I mentioned before, or having offline backups. Sometimes it's a hard call between patching a vulnerability quickly at the risk of reliability versus patching it slowly at the risk of keeping vulnerability open and available to an adversary. At the end of the day, it's a business decision that can be made easier if there are some safety nets deployed in terms of, for example, automated rollback if something goes wrong. And the most important part of the whole talk is actually culture. None of those principles that I mentioned before will matter a lot if there is no culture built around shared responsibility for security and reliability. Just like you can design systems, you can design a culture, and you can create incentives so that people who care about reliability, care about making systems secure, are rewarded for this. And leadership needs to incentivize doing the right thing and recognize those efforts. The reliability and security is just too prone to go unnoticed until the worst thing happens. And at this point, it's usually too late. So postponing caring about security and reliability might actually improve the initial velocity, but at the end, in the long term, it will almost always lead to increased costs of retrofits and actually a worse product at the end of the day. So it really needs to be, the products should be built secure and reliable by default, and not something as added as a bolt-on. So this obviously requires a commitment from the full life cycle. There are many ways to do it. The example that I can, a couple of examples I can quote that we use internally is we actually allow people to go into different roles for a limited amount of time. So you can join the security team for a couple of months. You can join a reliability team. We try to embed reliability and security engineers into the team so they're part of a team. They're not seen as external party that only shows up and criticize the design. We try to make this part of one team, one organization. The other are peer reviews. We try to review everything from code and config changes to system changes. And we are very explicit about expectations. We do not do any exceptions, even for senior roles or code owners. Everybody's going through the review process, and we do have some automated checks to assist the review. We do have a blameless postmortems if something goes wrong, and things go wrong quite often because this is life. We try to summarize, we try to find the root cause, we try to avoid assigning any blame to any individual, so to create this psychological safety space where we can actually focus on the problem and not assigning blame to anyone. And finally, we have a break-less option, so to ease the transition into the world where we have less freedom in the sense of making changes to a system because we need to ask another person for review. Maybe there's some fear that it will slow down the response time. We have a break-less mechanism that people can use that is heavily audited, but it is there in case of emergency. So I know it's been a lot of topics covered in only 30 minutes, and if you're interested in knowing more or exploring those topics that I just talked about, there is a good news. We wrote a book on this, 550 pages, so it's a pretty long book, but don't be intimidated. Read at least first 2 chapters, and you should get a clear idea of which parts of the book might be interesting to you. It's available for free actually online. You can go to our website and download Building and Secure and Reliable Systems. And on that note, I would like to thank you very much for your attention. And I would like to thank you very much to the organizers for an opportunity speaking at the conference. Thank you.